This webinar presents a review of the behavior of colorants during sugarcane processing. Color is considered to be an important quality parameter of raw sugar. In the sugar industry, the color of sugarcane processing streams is typically measured using the color method. This method involves the measurement of the absorbance of light at a specific wavelength by all compounds in a sugar sample. A color can be used to assess changes in color levels of streams throughout the sugar factory. However, it does not provide an indication of the different type of colorant compounds responsible for the visual color. The type of sugarcane colorants found in processing streams can be classed as either sugarcane plant-derived colorants or as factory-produced colorants. The sugarcane plant-derived color contributing compounds include insoluble colorants, flavonoids, and color precursors. Factory-produced colorants include caramels, HADPs, melanoidins, and melanins. The main factors which determine the type and quantity of sugarcane plant-derived colorants in factory streams are the quality and variety of the cane being processed. Poor quality cane usually results in higher color levels in raw sugar. As a result, raw sugar color tends to be the lowest in the middle of the season when the quality of sugarcane being processed within each variety is superior. With everything else being the same, processing fresh, mature, and well-topped cane with no brown leaf produces the best quality raw sugar. The sugar factory can be divided into 4 major processing sections: extraction, clarification, evaporation, and crystallization. These operations are controlled to optimize extraction and recovery and to produce high-quality raw sugar. In the sugar factory, there are many process control factors that need to be considered for the optimal performance of a sugar factory. The control parameters have different effects on the formation of the different colorant types. Caramels are compounds that are produced by the thermal degradation of sucrose. Caramelization reactions occur more intensely at high temperatures and when conditions are alkaline. High temperatures during diffuse extraction, clarification, and evaporation can result in caramelization reactions. Hexose alkaline degradation products, also known as HADPs, are colored polymers that are formed when hexose, glucose and fructose, are heated in alkaline conditions. Although the optimum pH for the formation of these colorants is 11, such high pH values rarely occur during sugarcane processing. The alkaline degradation reactions can occur at ambient temperatures, but intensify as the temperature rises to form dark-colored compounds. The low concentration and alkaline conditions of liming during clarification promote the formation of HADPs. Melanoidins are high molecular mass compounds produced by the Maillard reaction involving reducing sugars and amino nitrogen compounds. The factors affecting these reactions include the type of reactant species present in factory streams, pH, water content, and temperature. The rate of melanoidin formation peaks during juice evaporation when the temperatures are high, and these polymerization reactions continue during crystallization. Melanoidins are also formed at lower temperatures over long periods, such as during the storage of raw sugar, mainly the molasses film surrounding the sucrose crystal. Melanins are high molecular mass compounds formed by the enzymatic reaction of phenols with nitrogen compounds. These colorants are particularly difficult to remove in processing. Melanin formation occurs at temperatures between 18 and 55 degrees Celsius and in mildly acidic conditions when the pH value is between 4.5 and 8. Their formation is prominent during extraction of juice with a milling tandem where enzymes that originate from the cane are active, but they do not form to a great extent in diffusers and in subsequent processing stages, since the higher operational temperatures in those processing units denature enzymes. By understanding the characteristics of the various colorant types, we can gain some insight into their behavior during processing. An understanding of the behavior of colorants could assist factory operators with devising strategies to mitigate their formation in the factory. So to summarize, when looking at the different sections of the sugar factory, melanin formation is prominent during extraction. HADPs are likely to form during clarification, while caramels and melanoidin formation can occur during evaporation and crystallization. Let's now have a look at each processing section individually. Extraction of juice from prepared sugarcane is achieved with either a milling tandem or a diffuser. The South African sugarcane industry mainly uses diffusers. Shown on the top right corner is the typical operating conditions for extraction. Please note that the values presented throughout this presentation were collated from various literature sources and for different factories, and therefore are not the same as the normal ranges of variation within a particular factory. The color of diffuser juice is generally higher than juice from milling tandems due to the higher temperatures at which diffusers are operated. Milling juice usually appears greenish in color due to the presence of chlorophyll from cane, while diffuser juice is brownish in color as the higher temperature in the diffuser destroys the chlorophyll. However, after clarification, mill juice and diffuser juice appear similar in color since clarification also destroys chlorophyll. The extent of color increase during extraction is affected by a number of factors such as cane variety, climatic conditions, time of season, and the amount of tops and brown leaf. The formation of melanins is prominent during extraction of juice with the milling tandem. Caramels and colorants from brown leaves can form during diffuser extraction. Although the conditions of extraction, low Brix and slightly acidic conditions are not favorable for the formation of melanoidins, they can form to a very small extent in diffusers, since diffuser temperatures and in some cases pH are higher than in a milling train. There are a few process control strategies that can be implemented for minimizing color formation. Imbibition water temperatures that are too high can result in the acceleration of color formation reactions. Sanitation and regular cleaning of milling and diffusion equipment is required to limit bacterial activity. Bacterial activity can result in the degradation of sucrose to monosaccharides, which can result in the formation of colorant precursors. For sugar milling companies considering the production of a new product using a sucrose stream, color can be minimized by separating the juices from the last molds to produce a new product. A few Brazilian sugar factories producing ethanol are able to decrease mixed juice color and the subsequent color of raw sugar in this way. The purpose of clarification in a sugar factory is to remove non-sugar soluble impurities, suspended matter and colloidal particles. Among the impurities removed are colorant compounds. Liming prior to clarification also serves to increase the pH of the sugar stream in order to minimize the rate of sucrose inversion, which limits color formation later in the process. The insoluble sugarcane plant-derived pigments are removed during clarification. It has been reported that an Akumsa color change of ±5% occurs over clarification. Although some colorants are removed during clarification, the low concentration and alkaline conditions of this unit operation can cause hexoses to degrade and the formation of HADPs may occur. The process control strategies for minimizing color formation during clarification include maintaining a constant temperature and pH value, utilizing the shortest residence time possible and the correct addition of chemicals. Overliming during clarification can cause excessive scaling in the evaporators and promote the formation of colorants from the alkaline degradation of glucose and fructose. The evaporator station is the location in the sugar factory where juice is exposed to the highest temperatures, and therefore it is expected that color formation would be prominent in this unit operation. The increase in color during evaporation is usually approximately 8%, with the Maillard reaction and caramelization being the main contributors to color formation. Evaporator stations in the sugar factory were designed to limit the maximum juice temperature to below 120 degrees Celsius in the first effect, and thereafter the temperature gradually decreases across the remaining effects to a final temperature of approximately 60 degrees Celsius. Poor circulation can cause localized overheating of the juice, and this can lead to caramel formation. Long exposure times of the juice in the evaporators can lead to inversion of sucrose and subsequent color formation. The residence time can be managed through level control and by reducing scaling on heating surfaces. Crystallization is the most critical process for color control in the sugar factory. This step is an efficient means of separating colorants by crystallization of relatively pure sucrose, while leaving most of the impurities, including colorants, in the molasses mother liquor. In South African sugar factories, a 3-boiling partial remelt scheme is generally used during crystallization. Sugar produced in this way usually has 3.5% less color than a conventional 3-boiling system. For factories having a back-end refinery, there is an additional color load incorporated at the A station of the raw factory as a result of the 4th run of refinery stream entering the crystallization process at this stage. The Maillard reaction occurs during the sugar crystallization process, particularly during low-grade purity boilings due to the long retention times and the presence of impurities. This formation of melanoidins continues in the crystallizers and during the storage of molasses. Caramelization reactions also occur during crystallization when mesquite is in contact with heating surfaces. During the crystal formation and growth stage of the crystallization process, colorants remain mainly in the mother liquor, but a small quantity will be integrated into the structure of the sugar crystal. There are 3 ways in which color can be incorporated. Co-crystallization with sucrose. It is important that this be avoided because once colorants are incorporated into the sucrose crystal lattice in this way, they can only be removed by dissolution of the crystal. High molecular mass polysaccharides have a high tendency to co-crystallize with sucrose. Coating of the crystal surface. This is presented as a molasses film surrounding the surface of a sugar crystal and can be reduced by washing sugar in the centrifuge or by affination. Trapped in liquid inclusions in the crystal. Colorants trapped in this way result from uncontrolled rapid crystallization. This is considered a minor problem, since correct boiling practices would eliminate this mechanism of color incorporation. Certain colorants are incorporated into the sugar crystal to a greater extent than others. Shown here is the incorporation capacity of different colorant types as reported by Bento. The molecular mass and pH of a particular colorant has an effect on its tendency for incorporation in the sugar crystal, with higher molecular weight colorants and neutral polymeric colorants more readily included in the raw sugar crystal. Color formation can be limited by maintaining low boiling temperatures and keeping the amount of recycled remelt to a minimum. Low purity mesquites require longer residence times due to the slower crystal growth rate because of higher viscosities. This extended residence time results in high C mesquite colors. Although reducing the residence time would result in reduced color formation, this might mean sacrificing the benefit of improved exhaustion. In contrast, Smith reported that high exhaustions, particularly of A mesquite, contribute to low sugar colors since the recirculation of impurities is reduced. It is important that crystallization conditions produce sugar crystals with an optimum size, particularly in the A station. The larger surface area of smaller crystals results in a higher quantity of highly colored molasses film surrounding the sugar crystal. The bulk of the impurities in the raw sugar are located within the molasses film surrounding the crystal. It is therefore crucial that the centrifugation process is performed efficiently. Strategies for achieving optimal separation efficiency include a well-designed, operated and maintained centrifugal station. It is possible to reduce the color of sugar by washing crystals during centrifugation to remove a proportion of the high color molasses film that surrounds the sugar crystal. However, it is essential to monitor the washing efficiency since extended washing has the risk of sugar loss by dissolution, resulting in reduced exhaustion and increased recirculation. So that summarizes the behavior of colorants through the different operational stages of the sugar factory, as well as a few operational strategies that can be implemented for minimizing color formation. Different types of colorants contribute to the measured color of sugarcane processing streams. Various processing conditions of the sugar factory influence the nature and fate of colorant compounds in sugarcane processing streams. An understanding of the behavior of colorants throughout processing could assist factory personnel with devising strategies for maintaining and mitigating color formation in sugar factories. The SMRI is undertaking a research project for the identification of colorant types present in sugarcane processing streams. Shown here is a poster that was presented at the SASTA 2019 Congress, which detailed the exploratory project which aims to provide fundamental knowledge and insight into the nature, origin, and likely fate of colorants present in factory streams. It is envisioned that the project will provide solutions to color-related challenges that sugar factories experience. The project was initiated in 2019, and some of our project highlights are the following. We firstly explored analytical techniques, particularly spectroscopy. The main findings were that the spectral differences between streams indicate the possibility of using spectroscopy to distinguish between colorant types. We then focused on the use of a combined chemometric spectroscopic approach. The preliminary results were an encouraging progression towards determining the viability of a spectroscopic chemometric approach for the rapid analysis of colorants. The details of the research undertaken can be found in SMRI Technical Notes and Reports, which is available to all SMRI members. Currently, we are undertaking further investigations to assess how a combined spectroscopic chemometric approach can be further developed to provide factory operators with tools to manage the color levels of factory streams to consistently produce raw sugar having appropriate color levels. So that brings us to the end of the webinar. I just want to say thank you for your attendance, and we hope you enjoyed the presentation and learned more about the behavior of colorants during sugarcane processing.